Good morning. So, as I promised last time, let's go over more examples with problems related to the Legendre equation, and then maybe some hints on the homework, and we'll see how much time we have left. This might be either the last lecture or maybe there will be one more. We'll see, depending on the discussions we have online during our office hours. So, but at the very least, we'll have to go over an example of each type of the boundary conditions studied in this chapter. So last time, remember, one of the boundary conditions was a zero temperature at the bottom of the hemisphere. So that was like a Dirichlet homogeneous condition. And this example right now is an example in which you don't have any other boundary conditions, just because of the shape of the object, a full sphere in this case. So the only boundary is given by the exterior of the sphere. So the only condition, there's only one condition to be made, because there's only one boundary, so to speak, just given by the surface of the sphere. And that can be non-homogeneous. So you can have problems in spherical coordinates in which there is no homogeneous condition. I think the book mentions these situations like no boundary conditions, but that refers to the Sturm-Liouville problem. So when you do the separation of variables, the Sturm-Liouville problem will have no boundary conditions. So the object, as I said before, it's a full sphere, or a ball to be more precise, of radius c. So that means the domain for little r is 0 and c. And we want to find the steady state temperature. So we assume that the temperature stabilizes with respect to the time t. And the only extra condition is that on the exterior of this ball, so u of c, right? So u of c theta is equal to some prescribed temperature that may still depend on theta. This is what you see in many problems in the book, because again, the integrals required to compute in order to find the Legendre series of this function are not easy to compute. And you give the answer in terms of an integral that you don't actually compute it. So notice that from a physical perspective, that's all you need, right? I mean, if the temperature is to be stabilized in the long run, the only thing you need to specify is what happens on the boundary. And that's the only condition you need in this case. So if you proceed with the separation of variables, just like before, remember the drill. If you want, you can do it again just to see how it goes, but it's the same process. So you assume that u of r theta is a function in little r times a function in theta. And because you have a full sphere, theta varies between 0 and pi. Remember how theta is measured from the positive z-axis all the way to the opposite side, so from 0 to pi. And then the Sturm-Liouville problem will be the modified Legendre equation, sine of theta h prime of theta prime plus lambda sine of theta h of theta equals 0 without any extra conditions. And the equation in r squared r double prime plus 2r r prime minus lambda r equals 0, which is a Cauchy-Euler equation. Now it's time to look again on the formula sheet, and let me actually look myself on that formula sheet. You want to scroll down to the third page, where it says, after remark 1, where it says eigenvalues and eigenfunctions of Sturm-Liouville problems involving the Laplacian in spherical coordinates. So you are basically under condition A. There is no boundary condition on the interval 0 pi, which means the eigenvalues are all lambdas. So the eigenvalues are lambda equals n times n plus 1, with n from 0, 1, 2, and so on. So all the eigenvalues, including the even and the odd ones. when I'm talking about, again, even or odd, I'm talking about the first n here, because obviously if you multiply n with the next number, lambda will always be actually an even number, because it's a product of two consecutive natural numbers. I'm talking about whether n is even or odd. So these are the eigenvalues, and the eigenfunctions will be all Legendre polynomials. So the eigenfunctions hn of theta will be Pn of cosine of theta. So the all Legendre polynomials evaluated at cosine of theta. Go back to the now to the equation in R. You're going to replace to R prime lambda with n times n plus 1, and the characteristic equation, remember, of this Cauchy-Euler equation, then let's use the characteristic equation in S, just to not confuse it with R. It's going to be S squared plus S minus n times n plus 1. So very similar to the one before, and this factors again into S minus n, S plus n plus 1. So for each lambda n, for each eigen, we can call this lambda n, I guess, for each eigenvalue, Rn of little r will be some constant r to the n plus some other constant r to the minus n plus 1. And just like before, because of continuity, you're going to have to assume Pn is equal to Bn is equal to 0, because otherwise this will go to infinity as r approaches 0. So very similar like the problem before. And maybe it's worthwhile to pause and look at the previous lecture just to see the difference, right? The only difference is that the lambda goes to the odd ones, 2n plus 1, 2n plus 2 in the previous exercise. Here it's a full sphere, so n goes to all natural numbers. Now the superposition principle, meaning that the steady state temperature will have the form of a series from 0 to infinity, an r to the n Pn cosine of theta. And the last thing to do is to find an by imposing the non-homogeneous condition. So now from u of c theta equals some function of theta, we get that the summation from 0 to infinity an c to the n. So notice there's that c to the n, which is part of the full coefficient of this series. C is a natural number, right? So, and then Pn cosine of theta, this needs to be matched with f of theta. So to find the an, that means we need to write f of theta in the same manner, namely Pn of cosine of theta inside Pn, like that. So you will have to write f of theta in the same manner as a Legendre series involving all Legendre polynomials. So this is the moment when you will say, what is this coefficient supposed to be equal to from the formula of the Legendre series coefficients? Just don't forget that that coefficient is not an. That coefficient will stand for an c to the n. Pay attention to this one, because some people get confused by missing this c to the n, and then they don't understand where that comes from in the answer. So now you simply look at the formula for the Fourier for the Legendre series coefficients on this interval 0 pi. So an c to the power n will be what is that? Let's see, 2n plus 1 over 2. The integral from 0 to pi. The function f of theta, Pn cosine of theta, sine of theta, d theta. I want to direct you to the handout on the Legendre polynomials. If you scroll further down, you will have this formula right underneath the Sturm-Liouville problem in in theta. So the entry is called Legendre series for Pn of cosine of theta. So that's again formula A, which gives you these coefficients. Now, this is as far, I mean, almost, not as far as you go. So an, now to get an by itself, obviously you divide by c to the n. Okay, so the answer for an is 2n plus 1 over 2, 1 over c to the n, the integral from 0 to pi, f of theta, pn cosine of theta, d theta. And that's why sometimes in the answer we have this c to the n popping up. I think, I don't remember exactly, I think the book might be a little bit confusing in this regard. I think they might sometimes denote by an. Yeah, I mean, yeah, pay attention to this thing. They sometimes denote an, the coefficient that results from this superposition. So they include c to the n in the actual coefficient. So don't worry about that. You can leave the answer in the form I gave you here. That's just basically what you consider to be an. So I think in the book, let me actually write it down so that it's clear enough. So in the book, an c to the n is renamed or denoted by an. I think they use slightly different notation. What's important is to understand how the process works, right? So I mean, once you find an, you can consider the problem solved at that moment. So now, what if you have to solve this integral? So remember, I can't really ask you to do that unless f is a constant, or maybe leads this integral to x to the power 1 or 2. I could, and if that happens, I forgot sine of theta here, sorry about that. So there's another sine of theta in this integral. So if you have to solve this integral, typically you do this by substituting x with cosine of theta. So I'm going to do an example on the next page immediately. But for the most part, we leave the answer in that form unless we have to compute this integral. So let's see what happens if you actually have, we're going to do probably a second part on this, and then we're going to comment on some of these results, what happens if you have an actual function. But let me do one more line on this part, and then we're going to continue with the second part. So let's say, just like before, that f of theta happens to be a constant. So let's say f of theta is equal to, well, no, let's do a different one. Let's say f of theta is cosine of theta to the power 2, just to make that integral look nice when I make the substitution. So this could be a legitimate question, though it's not going to be easy, but still doable. This could be a legitimate question in the sense of actually finding these coefficients. So if f of theta is cosine of theta squared, you can go ahead and actually compute this coefficient by actually evaluating this integral in terms of theta. So notice that again I chose this to be cosine of theta squared just because once you do the substitution, x equals cosine of theta, this integral becomes from -1 to 1 x squared pn of x dx. So do the substitution on your own. Compute dx as minus sine d theta, plug in x for cosine of theta, and then you end up with x squared pn of x. Because from what we learned, these are the types of integrals that we can reasonably do by hand, because we have those recurrence formulas. Though again, this will be still a rather long problem, because you have to use those recurrence formulas several times. So on the next part, I'm going to actually do the integral for f of theta equal to a constant, because I want to comment on some physical insights that you get when you look at what the solution is. So stay tuned for the second part.